Hi, here we have a video on periodicity, in particular period 3. Now what periodicity means strictly is that characteristics like physical properties or chemical properties, they repeat each other cyclically. But what we really want to study here is the trends across period 3 in atomic radius, and also the melting points of those elements across period 3, and also their first ionization energies, the amount of energy that's required to pluck off the first electron, the outer electron, from one of their atoms for each of the elements across period 3. So that's what we're going to do. Start off with, let's have a look what elements we're talking about. Okay, let's have a look at a periodic table. Here we have the top half of a periodic table, and of course this is period 1 going across the top row. Period 2 from lithium to neon, and the period that we're interested in, period 3, is this one here, going from sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. That's what we're interested in, and let's have a look at the actual elements. Here we've got sodium down here, and magnesium and aluminium. This is actually silicon. We've got phosphorus, we've got white phosphorus here and red phosphorus here. We've got sulfur, chlorine. I'm not sure if you can see the green tinge in this gas tube, and you certainly won't see argon on the end. In a little bit more detail, here's a picture of what could be any metals really, are they? These are actually magnesium and aluminium. Sodium looks similar, shiny silver metals, so all of the sodium, magnesium, aluminium, they're the metals. The rest are non-metals, starting with silicon. Some people might describe silicon as a metalloid. That's a picture of silicon. That's what silicon looks like in its elemental raw form. Then here's some phosphorus and sulfur. There we've got some red phosphorus in the tube and some sulfur on the looks like a little dish, and again we've got the gases chlorine and argon there at the end. Okay, so that's the elements we're dealing with. I think what we're going to start with now is have a look at the trend in atomic radius as we go across from sodium all the way across to argon. So here's an actual statement of the trend. The atomic radius as you go across period 3 decreases, so it actually gets smaller. Which might seem odd because certainly the mass of the atoms is going to increase as you go along. You're adding one proton and neutrons as well as you go along. So the mass is going to increase, but the size decreases. But first of all, let's establish what we mean by size, and in particular atomic radius. The atomic radius, given by this diagram I've just flashed up here, is half of the distance between two adjacent nuclei. Right, so we've got one nucleus here, another nucleus here. So the distance between the two nuclei is that one, and so our atomic radius is half of that distance. So that's what we mean, and that's what we're comparing as we go for each of the elements as we go along the period. For a metal, they don't overlap. This is more like what a covalent bond would look like. But for a metal, you would have an ion, let's say it was a sodium 1+ ion, and that would be pretty close to another sodium ion with the electrons delocalized around the place, in which case we're still dealing with half of that distance between the nuclei. So let's have a look at this. This is a chart where the atoms are drawn to scale. So you can see, as we say, on the left, sodium is the biggest, even though it's the lightest. And that has an atomic radius of 0.18 nanometers. So all of these units, the units of all of these measurements are in nanometers, and you might remember that nanometers is 10 to the -9 of a meter. And so we're getting smaller as we go along, all the way along to argon, which is the smallest atom. Okay, now we're going to have to explain why that is. And so why don't we have a look at the nuclear charge, because that's the main thing. As we start off with sodium on the left hand side, so here's sodium, and you can see we've got 11 protons in the nucleus. And then magnesium's got 12, aluminium's got 13, etc. Until we get along to argon, which has 18 protons in the nucleus. All right, so argon has got a much more positive nucleus than sodium has. And so that's one factor. So a more positive charge in the nucleus is going to attract any electrons to itself more strongly than a less positive nucleus. And what's more, all of the electrons, as you go along the period, all of the electrons that are being added into the same shell. So if we have a look at this outer electron for sodium, you can see that's going into the third shell. That's 1, 2, and 3. For magnesium, we've got 2 electrons, but still in the third shell. For aluminium, we've got 3, of course, in the third shell, etc., etc., until we get to argon, where we've got 2, 4, 6, 8 electrons, but all in the third shell. All right, so the explanation of the decrease in size of the atomic radius is that the nuclear charge increases as you go along the period. However, the electrons are added into the same shell, the third shell, in this case in period 3. So there we have it. We can move on to another trend now. Yes, and that trend, or in fact pattern, is the trend in melting points. And the pattern in the melting points and the boiling points depends on the bonding between the atoms in the element. Okay, so let's have a look at the chart that gives us the trend. So this is melting points on the y-axis, an atomic number on the x-axis. So we're just going along the period in the same way, from sodium to argon again. And you can see that we've got two sort of trends. The first one is an increasing trend, and the second one is a decreasing trend. And if we looked at boiling points, you'd see some sort of trend like that as well. So the boiling point's a similar trend. And we're not going to get too hung up by the little blip here for aluminium, why it doesn't really follow a very straight line between sodium and silicon. But what we want to do is we want to explain first the fact that sodium, magnesium, and aluminium, they are all metallic. And so the bonding between those as metallic bonds, which are pretty strong bonds. And so let's have a little picture of a metallic bond. So here we've got magnesium and aluminium. So magnesium, you'll remember, is a magnesium 2+ ion, and you've got, for each magnesium atom, you're going to have 2 delocalized electrons floating around, whereas aluminium makes a 3+ ion, so you're going to have more electrons delocalized. And so, however, with sodium, you've only got a 1+ ion, so you're going to have a sodium 1+ ion and 1 electron delocalized for each of the 1+ sodium ions in the metallic structure. Right, so first point is that metallic bonds are pretty strong, and so our melting points are quite high, and sodium is the least high of those metals because the sodium ions make 1+ ions, and you've only got 1 delocalized electron per atom, in which case the electrostatic attraction is going to be slightly less. And what's more, the size of the ions are bigger, and so the distances are greater, so that weakens the attraction between the metal ions. Okay, and you get a stronger attraction for a 2+ ion, as in magnesium, and an even stronger attraction still for the 3+ ion, like aluminium, because you've got more positive charge and more delocalized electrons, and therefore more bonds. Okay, that explains the first 3, the metals. Now, silicon, of course, as we can see on the graph, has the highest melting point of all, and That's because it's got very strong covalent bonds. It's a giant covalent structure. Let's have a look at it. Here we've got silicon, and each silicon atom is bonded to 4 other silicon atoms. It's in group 4. And the bonds between those silicon atoms are very strong covalent bonds. And so that's what makes silicon's melting point so high, is that it takes such a lot of energy to break those strong covalent bonds, and that's why it appears where it does on the chart there. Now, however, when we go on to the rest, or at least phosphorus, sulfur and chlorine, we're also talking about covalent bonds. However, we're not talking about giant covalent structures. We're talking about simple molecules. So for those next 3, phosphorus, sulfur and chlorine, we're talking about simple molecules, and that's why those melting points and boiling points are so low. Chlorine about minus 100 degrees, and phosphorus and sulfur only just solids at room temperature, easy to melt, both of them. So simple molecules, you remember from the bonding section that although the bonds within the molecule are strong covalent bonds, actually what determines the melting and boiling points is the forces between the molecules, and they are only intermolecular forces. So van der Waals forces or dipole-dipole forces. So let's have a look at the molecules to explain some more detail here. So we've got phosphorus and sulfur. You actually see phosphorus with a lower melting point than sulfur, and that's because the standard state of phosphor is a P4 molecule. Right, so these bonds here are strong covalent bonds, but they're not the ones that are being broken when it melts. What's being broken is, of course, the intermolecular forces between molecules. Okay, and sulfur is a bigger molecule. Sulfur is an 8-atom molecule, and that being a larger molecule will have stronger van der Waals forces, and that's what explains this slight difference in melting point there between phosphorus and sulfur. And chlorine is smaller still. So chlorine is a diatomic molecule. We can see here in green, this is chlorine, and we've only got 2 atoms in this molecule, and that's why its melting point is even less. Whereas argon is not a molecule at all, it exists as an atom, and so that's the smallest of all, and almost no van der Waals forces there. So that's what makes those 2 elements gases at room temperature, and it makes the melting point of argon especially low. So there we have it. There's the pattern in melting points, and it's all to do with bonding between the atoms in the elements. Now we move on to ionization energies, and we say here that they generally increase across period 3, and in fact they follow the same pattern across all the periods. So they generally increase. Why have I used that word generally? Well, because there's a couple of blips that we need to be able to explain. So let's have a look. Here is the trend. Again, we're going from sodium right across to argon, and you see a general increase, but with 2 blips here and here. But first of all, let's explain the general increase. And the general increase is explained by the fact that the nuclear charge increases by 1 each time as you go from sodium to magnesium to aluminium to silicon, etc. And that extra proton in the nucleus holds the outer electron slightly more strongly, so it's more difficult to remove, it takes more energy to remove, and that is the first ionization energy. It's the energy required to remove that first outer electron. So we can see that here pictorially. We've got 11 protons in sodium, and we've got 18 protons in argon, but we're only removing an electron from the same shell. All right, so that would be that electron that I've just ringed there in sodium is the electron that we would remove for the first ionization energy of sodium, and let's say it's this one. It could be the other outer electron from magnesium, but it's in the same shell, but we've got an extra proton to hold it a bit more strongly. That's why that increase there happens, and it explains the general increase from left to right. Now what we want to do is we want to explain the first little blip. Why does aluminium, why is the first ionization energy of aluminium less than that of magnesium? So let's find, this is aluminium here that I've just underlined, this one here, and this is the electron we're removing. It's the first electron to be removed in the outer shell, the third shell. We've got 13 protons here, whereas magnesium's only got 12. So wouldn't you expect an ionization energy, say maybe up here, so that we'd be following that general trend? Why is it not up there? Why is it down here instead? Well, that's explained by the electronic structure. So let's have a look at the electronic structure first of magnesium. Okay, so magnesium obviously is 1s2, 2s2, 2p6. So first and second shells are completely full, and magnesium is the second element along period 3, so it's got two 3s electrons. That's them marked here. They go into the 3s orbital, and on this energy chart, what we've got here is we've got this line here, which is the energy that is required to actually remove the electron. So the difference between the energy level of a 3s electron and the energy required to remove it is that, whereas, and what we're going to do now is we're going to compare the same energy difference for aluminium. And here it is. Here we've got aluminium. This is aluminium, and again we've got first and second shells full, but this time we've got 3 electrons to put into orbitals for aluminium, and of course the first 2 are going to go into the 3s orbital, and the third one is going to go into 3p, and the 3p orbital is slightly higher energy level than the 3s, which means that the energy difference between the energy level of the 3p orbital and the energy required to remove it is less, and that explains why, although you have an extra proton, the ionization energy is actually less because you're removing an electron from a 3p orbital, not a 3s orbital as in magnesium. Okay, hopefully that was clear. What we want to do now is on the next slide explain the other blip between phosphorus and sulfur. Why doesn't that actually follow the same trend? Why isn't sulfur up there on a sort of more linear trend between sodium and argon? Let's do that on the next slide. So let's get a clean version of that trend. And what we're trying to explain is why the first ionization of sulfur is not about there, which is where it would be if you were following the linear trend. Why is it less than we might expect? Well, again, we're going to have to look at the electronic structure. So let's bring that up. So here we've got, first of all, the electronic structure of phosphorus. Okay, so again, first energy level and second energy level all full, but phosphorus is in group 5, and so we've got 5 electrons to put into the third shell. First 2 are going to go into the 3s, and that leaves 3, and as you know we've got 3 3p orbitals. So the first one goes in the first 3p orbital, and according to the London bus rule that you remember, the second one needs to go into the other orbital, and the third one needs to go into the third orbital. So as you know, the electrons occupy orbitals singularly before they pair up. Okay, so that explains phosphorus, that describes phosphorus more like, and what we're going to do now is compare that to sulfur. So as we go along from phosphorus to sulfur, we're going to add another electron. Okay, so first energy level, second energy level is all the same. But this time we've got 6 electrons to fill instead of 5. Sulfur's in group 6. And so the first 2 are going to go in 3s, just like with phosphorus. And just also like phosphorus, the first 3 go singularly into the 3p orbitals. But the next one, it has to pair up. All right, so it goes in. It could go into any one of these 3p orbitals. So let's put it in this one here. It has to pair up. Okay, so those 2 electrons in this orbital are very close together and end up repelling. So let's write down repulsion. So there is a bit of repulsion between those 2 electrons, and that repulsion explains why the first ionization energy is less than we might expect. So that repulsion means that the first ionization of sulfur is actually slightly less than the first ionization of phosphorus, despite the sulfur nucleus having 1 extra proton in it compared to phosphorus. Okay, so that's the second little blip. So there's 3 things generally to remember about ionization energies across period 3. First is a general increase as we increase the number of protons in the nuclei. Second thing is the explanation of why aluminium is less than expected because of the 3p electron. And the third thing to remember is for sulfur, why that is less than expected, and that's because of the repulsion of the electron that's been paired up in a 3p orbital. Okay, good. That's just about it. We might just, while we're on ionization energies, recap a little bit from atomic structure on the next slide. So here we're going to say successive ionization energies. So what we're talking about now is first ionization compared to second ionization compared to third ionization energies, etc., until you've removed all the electrons of an atom. Right, so successive ionization energies of an element, that gives us information about the electronic structure of that element. So let's have a look at some data here. So we're having to take a log of the ionization energy to see the pattern, otherwise the data wouldn't really show us anything. So what we're doing is we're removing 13 electrons, so that could give us a clue as to what it is. If it's an atom, then if it's got 13 electrons, it's got 13 protons, which makes this aluminium. And let's just check that it's aluminium. If it's aluminium, it's got 3 outer electrons, hasn't it? And the first 3 outer electrons are going to be the easiest to remove, so they're going to have the lowest ionization energy. And that's what we've got here. So we've got 3 electrons in the in shell 3, in the third shell. And they're lowest down in this trend, and that's as we would expect because they're in the highest energy levels, and so they're going to take least energy to remove. And they're further because they're furthest away from the nucleus. But then there's quite a jump here, isn't there? There's quite a jump from third to fourth. Why is that? That's because the next electron that we're going to remove, the 4th electron, is actually coming out of shell 2. And so that's a lot closer to the nucleus. The nuclear charge is still the same. We're not changing the number of protons in the nucleus. So there's going to be a lot of more energy required to extract that 4th electron. And as we then remove the 5th electron for here and 6th electron for here, the ionization energy increases little bit by little bit because we're only taking an electron from the same shell. But when we have taken all the electrons, right? So when we've taken all of these electrons out of the second shell and we want to remove the next electron, we have to go deep down into the atom to the first shell, and that's why there's another leap in ionization energies there, because here we are taking the 2 electrons from the 1s shell, subshell. So the thing to note here is that because you can see those leaps in ionization energy, that gives you some evidence that these electrons are arranged in shells, and the first shell has 2 and the second shell has 8. And aluminium, for example, has 3 in its outer shell. So that's what we can sort of deduce from this chart about aluminium. Let's have a look at one more. Looks like we're removing 11 electrons in total, and so if it was an atom, if it was an ion it'd be different. If it was an atom, it would also have 11 protons, which would make this sodium. Sodium, as we'll probably remember, is in group 1, which has 1 electron in its outer shell. And hey presto, that makes sense because our leap is after removing 1 electron. All right, so that's good. So we've got 1 electron in the outer shell. Then we've got a leap before we start extracting the electrons from shell 2, and we do that for all 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. We do that for all 8 electrons in shell 2 before there's another leap in ionization energy before we take the 2 electrons in shell 1. So similar story, but you can see that we've only got 1 outer electron for sodium, which is what we would expect. Okay, a very quick little recap about successive ionization energies. That brings us to the end of this little video. But lastly, let's just make sure that we covered off all we wanted to. We had a look at the trend in atomic radius across the pattern, across the period, and saw it get smaller because of the increasing nuclear charge. We saw a trend in melting points and related those to the bonding between the atoms in the element. So we had metallic bonding, we had a giant covalent with silicon, and we had simple molecules with phosphorus and sulfur and chlorine, and then we had single atoms as well with argon. Then we had a look at the first ionization energies, saw an increasing trend in first ionization energies generally as the nuclear charge increased across the period, but we saw a couple of blips there as well, and we explained those. So 1,